Every galaxy in the observable universe is racing away from us. The fabric of space itself expands, carrying distant stars beyond our cosmic horizon. We've known this for nearly a century. We understand it. We've measured it. But something is wrong. Hundreds of galaxy clusters, structures containing thousands of galaxies each, spanning millions of light years, are moving in the same direction. Not just expanding with the universe, not following the patterns we predict. They're being pulled, all of them, toward the same point in space. The velocity? Nearly 2 million miles per hour. The cause? Unknown. This isn't the gentle expansion of space-time we've grown comfortable with. This is a coordinated movement of matter on scales that defy our models of cosmic evolution. Something beyond the edge of the observable universe, something we cannot see, cannot directly measure, cannot explain, is exerting gravitational influence across billions of light years. What if the universe we observe is just a small region of something vastly larger? What if forces from beyond our cosmic horizon are shaping everything we see? Today, we journey through evidence that challenges everything we thought we understood about the structure and fate of the cosmos. Prepare yourselves. We begin. In 2008, a team of astronomers led by Alexander Keshlinsky at NASA's Goddard Space Flight Center was studying the cosmic microwave background, the faint afterglow of the Big Bang that permeates all of space. They weren't looking for anything revolutionary. They were conducting routine measurements of galaxy cluster velocities, attempting to map the fine structure of the early universe. What they found defied expectations. Galaxy clusters are the largest gravitationally bound structures in the universe. Each one contains hundreds or thousands of galaxies, all held together by gravity, collectively weighing as much as 1,000,000 billion suns. These clusters move through space, their velocities influenced by the expansion of the universe and the gravitational pull of nearby matter. The team was measuring something specific, the kinetic Sunyaev-Zeldovich effect. When cosmic microwave background passes through a galaxy cluster, it interacts with the hot gas between galaxies. This interaction leaves a distinctive signature, a slight temperature distortion in the microwave background. By analyzing these distortions, astronomers can calculate how fast each cluster is moving and in what direction. The standard model predicted random motion. Galaxy clusters should move in various directions, their velocities determined by local gravitational effects and the overall expansion of space, some toward us, some away, some perpendicular to our line of sight. On average, these motions should cancel out, showing no overall pattern. But that's not what the data showed. 709 galaxy clusters, spread across vast stretches of sky, exhibited a collective motion. They were all moving in approximately the same direction toward a region of space in the constellation Centaurus, not just drifting slowly, racing at nearly 2 million miles per hour, roughly 3 times faster than our own Milky Way orbits within the local galactic group. Keshlinsky and his colleagues checked their calculations. They rechecked their data. They searched for systematic errors. The pattern remained. They published their findings with a simple, evocative name: dark flow. The astronomical community reacted with skepticism, and for good reason. According to our best cosmological models, nothing beyond a few 100 million light-years should influence the motion of galaxy clusters. Gravity, while infinite in range, weakens dramatically with distance. The observable universe appears remarkably uniform on large scales, a consequence of cosmic inflation, that brief period immediately after the Big Bang when space expanded faster than light, smoothing out any irregularities. This uniformity is no accident. Inflation theory predicts it. The cosmic microwave background confirms it. On scales larger than several 100 million light-years, the universe looks essentially the same in every direction. Matter is distributed evenly. No massive structures exist that could pull galaxy clusters across billions of light-years. Yet here was evidence suggesting coordinated motion across distances of 2 to 3 billion light-years. The gravitational pull required would be immense, equivalent to tens of thousands of galaxy clusters, all located beyond the edge of the observable universe. The implications were staggering. If dark flow was real, it suggested one of several possibilities, each more troubling than the last. Either our models of cosmic structure were fundamentally incomplete, or the universe extended far beyond what we can observe, or the early universe wasn't as uniform as inflation theory predicted, or something else entirely, something we hadn't yet imagined was shaping the cosmos on scales we'd never considered. Critics emerged immediately. Some argued the effect was a statistical artifact, a pattern that appeared meaningful but resulted from random fluctuations. Others suggested systematic errors in measuring the microwave background distortions. Still others claimed the effect, if real, could be explained by known structures within the observable universe, no exotic physics required. Kashlinsky's team prepared for a long battle of verification. But the evidence forces us to confront an uncomfortable possibility. We might be living in a universe far stranger, far larger, and far more complex than our theories allow. The first independent confirmation came in 2010. Kashlinsky's team expanded their analysis to include over 1,000 galaxy clusters, using improved data from the Wilkinson Microwave Anisotropy Probe. The dark flow persisted. Same direction, same velocity, same inexplicable coordination. The motion wasn't subtle. Galaxy clusters were traveling at 600 to 1,000 kilometers per second in excess of the cosmic expansion, velocities that shouldn't exist given the distribution of matter within the observable universe. To put this in perspective, our Sun orbits the galactic center at 220 kilometers per second. These clusters were moving 3 to 4 times faster, and all in the same direction. More troubling still, the velocity remained constant across different distances. Clusters located 1 billion light-years from Earth showed the same flow pattern as clusters 3 billion light-years away. This consistency violated expectations. If the pull came from structures within the observable universe, clusters at different distances should show different velocities. Stronger effects for objects closer to the source, weaker effects for distant objects. Instead, the data suggested the source lay beyond the cosmic horizon, its gravitational influence uniform across the entire observable region. In 2013, the European Space Agency's Planck satellite, the most sensitive instrument ever built for studying the cosmic microwave background, provided new data. The Planck team initially published results contradicting dark flow, claiming their more precise measurements showed no evidence of bulk motion beyond what conventional models predicted. The controversy intensified. Two research teams, using different methods and different instruments, reached opposite conclusions. Either dark flow was real and Planck had missed it, or dark flow was an artifact and the original team had been misled by their data. But here's where the story becomes more complex. In 2015, researchers at the University of Durham analyzed the distribution of radio galaxies across the sky. Radio galaxies are among the most powerful objects in the universe, their emissions detectable across billions of light years. The team discovered something unexpected. These galaxies showed a preferred orientation in space. Their jets, massive outflows of material extending thousands of light years from supermassive black holes, pointed in similar directions across vast cosmic distances. This alignment made no sense. Galaxy orientations should be random, determined by the chaotic conditions during their formation billions of years ago. No force should coordinate the spins of galaxies separated by billions of light years. Unless those galaxies formed within a larger structure, one with its own angular momentum, one extending beyond what we can observe. In 2018, astronomers studying the local supercluster, the massive structure containing our own Milky Way, along with tens of thousands of other galaxies, measured its velocity through space. They found it moving at over 600 kilometers per second toward a concentration of galaxy clusters called the Shapley supercluster. But the calculations didn't balance. The Shapley supercluster, while massive, didn't contain enough matter to account for the observed velocity. Something beyond it, something farther away, something more massive had to be pulling the entire local supercluster. The pieces were accumulating. Individual observations, each controversial on its own, began forming a pattern. Galaxy clusters moving together, radio galaxies aligned across cosmic scales, superclusters being pulled toward regions that couldn't explain their acceleration. But this represents just one piece of a much larger puzzle hidden in the structure of space-time itself. The most remarkable discovery involves the nature of the cosmic microwave background itself. This radiation, released 380,000 years after the Big Bang, when the universe cooled enough for atoms to form, provides our most pristine view of the early cosmos. It arrives at Earth from every direction, carrying information about conditions nearly 14 billion years ago. Its temperature varies by only 1 part in 100,000 across the sky, evidence of the extraordinary uniformity inflation theory predicts. But within those tiny variations lies a mystery. In 2011, researchers analyzing Wilkinson microwave anisotropy probe data discovered anomalies in the largest scale temperature patterns. The microwave background wasn't perfectly symmetric. It showed a preferred direction,
a cosmic axis along which temperature fluctuations aligned more strongly than probability allowed. Scientists call this the axis of evil. The name is tongue-in-cheek, but the implications are serious. These alignments shouldn't exist. Inflation should have erased any directional preferences, leaving the early universe with no special axes, no preferred orientations. Yet the data suggested otherwise. Here's the connection. The axis of evil points in roughly the same direction as dark flow. Coincidence? Perhaps, but consider the probability. The cosmic microwave background covers the entire sky. The chance that its largest scale anomaly would align with the direction of unexplained galaxy cluster motion approaches 1 in several thousand. Not impossible, but unlikely enough to warrant serious attention. Additional evidence emerged from studies of cosmic voids, vast regions of space nearly devoid of galaxies, spanning hundreds of millions of light-years. In 2017, astronomers discovered that the largest known void, the KBC void, appeared to be expanding asymmetrically. One side grew faster than the other, suggesting something external was pulling on its boundaries. The direction of maximum expansion? Aligned with dark flow. Then came observations of the Hubble constant anomaly. The Hubble constant measures how fast the universe expands, a fundamental number connecting distance and velocity for all cosmic objects. For decades, astronomers have measured this constant using two methods, studying the early universe through the cosmic microwave background and measuring distances to nearby objects like supernovae. These methods should give the same answer. They don't. The discrepancy has grown with improved measurements, reaching a point where systematic errors seem unlikely to explain it. The universe appears to be expanding faster locally than it did in the distant past, or alternatively, something is affecting our local region of space differently than the cosmic average. Several teams have proposed that dark flow might be connected. If matter beyond the observable universe pulls on our local region, it could affect how we measure cosmic expansion, creating an apparent discrepancy between early universe and late universe measurements. The evidence doesn't stop there. In 2020, astronomers discovered that the rotation curves of galaxies, the way their stars orbit around galactic centers, showed subtle alignments across distances of hundreds of millions of light-years. These alignments suggested that large-scale structures might preserve information about even larger structures, imprinted during cosmic formation. Every observation pointed toward the same unsettling conclusion. The observable universe might be embedded within something larger, something that shaped its evolution, something that continues to influence its motion. The evidence extends beyond dark flow into the realm of fundamental cosmic structure, challenging the assumption that the observable universe represents a fair sample of the whole.
To understand what might be causing dark flow, we must reconsider what lies beyond the cosmic horizon. The observable universe extends roughly 46 billion light-years in every direction. Not 14 billion, despite the universe being 14 billion years old, because space itself has been expanding. Beyond this horizon, light hasn't had time to reach us. We can't see what's there. We can't measure it directly. Our theories about cosmic structure are based entirely on what exists within this observable region. But the actual universe,
the whole universe is almost certainly far larger. Inflation theory, which explains why the observable universe appears so uniform, predicts that space expanded exponentially for a fraction of a second after the Big Bang. During this period, the universe grew by a factor of at least 10 to the 26th, likely much more. If this happened, the observable region represents just a tiny patch of a vastly larger whole. Think of it like standing in a flat field. The ground appears flat because you can only see a small area, but you're actually on the surface of a sphere, Earth, whose curvature only becomes apparent at larger scales. Similarly, the observable universe appears uniform because we're seeing a small, smooth patch of something with structure at larger scales. What lies beyond our cosmic horizon? Several possibilities emerge, each supported by different lines of evidence and theoretical reasoning. First, massive structures beyond the edge. If matter distribution continues beyond what we observe, there could be superclusters or even larger structures whose gravitational influence extends into our observable region. Calculations suggest that a mass equivalent to tens of thousands of galaxy clusters located beyond the cosmic horizon could account for dark flow's observed velocity. Such structures shouldn't exist according to standard inflation models, but inflation has variance. Some predict that density fluctuations in the early universe extended to much larger scales than previously thought, seeding the formation of enormous structures in the unobservable universe. Second, collision with another universe. Eternal inflation theory suggests that inflation never truly ended. It continues in most regions of space, spawning countless bubble universes, each with potentially different physical laws. Our observable universe would be one such bubble. If our bubble collided with another during cosmic history, the impact would leave signatures, asymmetries in the cosmic microwave background, bulk motions of matter, alignments of large-scale structures. Laura Mersini-Houghton at the University of North Carolina has argued that dark flow and the axis of evil could both result from gravitational interactions with neighboring bubble universes before inflation ended in our region. Third, primordial inhomogeneities. Standard inflation assumes the inflaton field, the hypothetical field driving inflation, was nearly uniform across space. But if it varied significantly, different regions would exit inflation at different times, creating variations in density and gravitational potential that extended beyond the observable universe. These variations would pull on matter within our cosmic horizon. Fourth, topology of space. If the universe is finite but unbounded, shaped like a three-dimensional analog of a sphere surface, matter could influence itself gravitationally across opposite sides of space. While most topological models predict a universe smaller than the observable region, which would create repeating patterns we don't see, some variants allow for larger spaces with subtle, difficult-to-detect signatures. The challenge facing theorists is that all of these explanations require physics beyond the observable universe, by definition, beyond direct verification. We can only test them indirectly through their predicted effects on what we can see. This forces us to reconsider fundamental assumptions about cosmology. We've built our models assuming the observable universe represents the whole, or at least a representative sample. But if dark flow is real, that assumption collapses. We're forced to confront the possibility that our theories, while accurate for describing local physics, miss crucial large-scale structures that shape cosmic evolution. The debate over dark flow's reality continues, but technology is catching up to the controversy. The European Space Agency's Euclid mission, launched in 2023, is mapping the three-dimensional distribution of galaxies across 10 billion light-years. Its precise measurements of galaxy positions and velocities will either confirm or rule out large-scale bulk flows. If dark flow exists, Euclid will see it with unprecedented clarity. The Vera C. Rubin Observatory, which began operations in 2024, surveys the entire visible sky every few nights, tracking changes and mapping cosmic structures with extraordinary precision. Over a decade, it will measure the positions of billions of galaxies, providing the largest three-dimensional map of the universe ever created. Any coordinated motions on scales of billions of light-years will become apparent. NASA's proposed SPHERX mission, scheduled for the late 2020s, will create a three-dimensional map of the universe using infrared light, detecting galaxies too distant for optical observation. This will extend measurements of cosmic flows to earlier epochs, potentially revealing when dark flow began and how it has evolved. But these observations serve a deeper purpose than confirming or rejecting a specific phenomenon. They probe fundamental questions about cosmic structure and evolution. If dark flow is confirmed, the implications ripple through cosmology. We would need to revise our models of inflation, potentially discovering new physics in the process. We would have direct evidence that the observable universe is embedded in something larger, opening questions about that larger structure's properties and extent. If dark flow is ruled out, we face different questions. What caused the initial observations? What systematic errors produced such a compelling pattern? And why do other anomalies, the axis of evil, radio-galaxy alignments, void asymmetries, appear to correlate with the same direction? Recent breakthroughs suggest we might not have to wait for spacecraft missions to resolve the controversy. In 2022, researchers at the Max Planck Institute for Astrophysics developed new techniques for analyzing gravitational lensing, the bending of light by massive objects. When light from distant galaxies passes through galaxy clusters, it distorts in characteristic ways. By analyzing these distortions across thousands of clusters, astronomers can measure not just their positions, but their velocities with unprecedented precision. Preliminary results from applying these techniques to existing data suggest bulk motions consistent with dark flow, though at smaller velocities than originally reported. The discrepancy might reflect different measurement methods, or it might indicate that dark flow's strength varies with cosmic epoch. In 2023, theoretical physicists proposed using observations of gravitational waves, ripples in spacetime from colliding black holes and neutron stars, to test for large-scale anisotropies in the universe. If space itself has a preferred direction of expansion or contraction, gravitational waves traveling different directions would be stretched or compressed differently. Future gravitational wave observatories might detect these subtle variations. The most speculative proposals involve using quantum entanglement to probe cosmic structure. quantum correlations between particles in different regions of space might preserve information about larger-scale gravitational fields, potentially revealing influences from beyond the cosmic horizon. While highly theoretical, such approaches could provide entirely new windows into the unobservable universe. What unites all these future investigations is a shift in perspective. Rather than assuming the observable universe is all that matters, cosmologists are developing methods to detect and characterize influences from beyond our horizon. We're learning to study the invisible through its effects on the visible. The implications extend beyond academic physics. If the universe is vastly larger than the observable region, if structures beyond our horizon influence cosmic evolution, then our understanding of the universe's fate must change. The heat death of the universe, the ultimate dissipation of all energy, might look different if matter beyond our horizon continues to exert gravitational influence. The universe's expansion rate, which determines whether it will expand forever or eventually collapse, might be affected by external masses we can't see. Even the search for extraterrestrial intelligence takes on new dimensions. If dark flow reflects structures that extend beyond the observable universe, then cosmic evolution might be fundamentally different in different regions. The conditions that allowed life to emerge on Earth might be relatively rare or common, depending on what lies beyond our cosmic horizon.
The most profound implications emerge when we consider what dark flow suggests about the nature of observation itself. Physics is built on the principle that we can understand the universe by observing it. We gather data, construct theories, test predictions, and refine our models. This approach has revealed atoms, decoded the genetic code, predicted the existence of black holes decades before we found them. It works because the things we want to understand are, in principle, observable. But what happens when the causes of observable effects lie beyond observation? Dark flow, if real, represents a crisis in epistemology. We measure its effects, galaxy clusters moving in coordinated patterns. We can characterize those patterns with precision, but we cannot observe the cause. It lies beyond the cosmic horizon, forever hidden by the finite speed of light and the finite age of the universe. Can we truly understand phenomena whose causes we cannot observe? This question isn't purely philosophical. It has practical implications for how we do cosmology. If influences from beyond the observable universe shape what we see, then our models, based on observable matter alone, will always be incomplete. We might develop theories that fit the data perfectly within our region of space, yet fail to capture the underlying physics because they miss crucial components outside our observational reach. Consider an analogy. Imagine aliens living in a sealed room, studying physics. They can measure forces, accelerations, and energies within their room with perfect precision. But they can't see that their room is aboard a spacecraft accelerating through space. They would develop theories explaining all their observations, theories that work perfectly for predicting phenomena within the room, yet fundamentally miss the larger context shaping their environment. We might be in that room. The observable universe might be our sealed chamber, and dark flow might be evidence of acceleration we can measure, but whose cause lies beyond our walls. Some theorists find this possibility liberating.
If the observable universe is just a small patch of something larger, then observed anomalies, dark flow, the axis of evil, the Hubble constant tension, might have simple explanations requiring no exotic physics. We're simply seeing edge effects from a larger structure, like how ocean currents in a bay reflect influences from the open sea beyond. Others find it troubling. Science progresses by explaining the unknown in terms of the known, the unobserved in terms of the observed. If we invoke unobservable structures to explain observations, how do we avoid falling into unfalsifiable speculation? How do we distinguish between legitimate inference and convenient postulation? The answer might lie in consistency. If structures beyond the cosmic horizon exist, they should influence multiple observable phenomena in related ways. Dark flow, the axis of evil, galaxy alignments, void asymmetries. If these all point toward the same direction, if they correlate with each other in ways predicted by models of larger scale structure, then we have evidence beyond any single observation. This approach mirrors how we've inferred other unobservable phenomena. We can't see dark matter directly, but we infer it from gravitational effects on galaxies, galaxy clusters, and the cosmic microwave background. We can't see the interior of the sun, but we infer its properties from the fusion products that emerge. Inference isn't speculation if it's constrained by multiple independent observations. But dark flow pushes inference to its limit. We're not just inferring properties of something we can't see, we're inferring the existence of structures beyond the boundary of possible observation. This raises a question that extends beyond dark flow to the nature of the cosmos itself. Is the universe fundamentally knowable? If the whole universe is vastly larger than the observable region, we're confronted with permanent ignorance about most of reality. We can learn everything there is to know about our local cosmic neighborhood, master every physical law that applies within the observable universe, and still know almost nothing about the universe as a whole. Some cosmologists embrace this limitation. The multiverse concept, which emerges naturally from inflation theory, predicts countless regions of space with different physical laws, most of them forever beyond observation. In such a universe, we can only hope to understand our local patch, the region causally connected to us. Others seek ways around it. Perhaps quantum entanglement preserves correlations that span beyond the cosmic horizon. Perhaps the laws of physics themselves contain information about global structure. Perhaps future theories will reveal connections we haven't yet imagined. The practical question is how we respond scientifically. Do we restrict cosmology to the observable universe, treating anything beyond as metaphysics? Or do we develop rigorous methods for inferring properties of the unobservable, accepting that some conclusions will always remain indirect? The answer likely involves both. We need caution about unfalsifiable claims, but we also need boldness in following evidence wherever it leads, even if it leads beyond observable boundaries. Dark flow forces this conversation because it sits precisely at the boundary. Its effects are observable, its cause might not be. Whether we embrace it as evidence of larger structures or reject it as systematic error, we're making a choice about what kinds of explanations we find acceptable in science. That choice shapes not just cosmology, but our relationship with the cosmos itself.
We began with a simple observation. Galaxy clusters moving in coordinated patterns, pooled toward a point in space we cannot see. What seemed like a straightforward measurement has become a window into profound questions about cosmic structure, the limits of observation,
and the nature of scientific knowledge. If dark flow is real, it tells us the observable universe is a small region of something vastly larger, something that shaped its evolution, something that continues to influence its motion. It suggests that the smoothness and uniformity we observe on large scales might be local properties, not universal ones. It forces us to consider that our theories, while accurate for describing what we see, might miss crucial components that lie forever beyond our horizon. If dark flow is an artifact, it still teaches us important lessons. It shows how subtle systematic errors can produce compelling patterns. It demonstrates the challenge of measuring tiny effects across cosmic scales. It reminds us that skepticism and verification are essential components of scientific progress. But regardless of dark flow's ultimate status, the questions it raises endure. We live on a planet orbiting an ordinary star in an average galaxy within an unremarkable region of the observable universe. That observable region contains roughly 2 trillion galaxies, each with hundreds of billions of stars, spread across 93 billion light-years. It is almost incomprehensibly vast. And if dark flow is correct, it's just a tiny patch of something larger still. The universe may be finite or infinite. It may be smooth on the largest scales or structured. It may be all we can ever observe or part of something that extends forever beyond our cosmic horizon. We don't yet know which of these possibilities is correct, but we're learning to ask the right questions, to develop technologies that can probe deeper, to construct theories that make testable predictions even about what we cannot directly see. The current scientific consensus remains uncertain. Dark flow divides the astronomical community. Some observations support it, others contradict it. Future missions will provide definitive answers, or at least better questions. What remains certain is this: the universe is far stranger than we imagined, far larger than we can observe, and far more wonderful than we can comprehend. Every answer reveals new mysteries. Every discovery opens new frontiers. Somewhere beyond the edge of the observable universe, beyond the cosmic horizon where light cannot reach us, something might be pulling on everything we see. Whether that something is a massive structure, a neighboring universe, or something we haven't yet conceived, it reminds us that our knowledge, while vast, remains incomplete. The universe is vast, the mysteries are endless, the journey continues, and we flow with it toward destinations we cannot see, seeking understanding we may never fully achieve, driven by the most human of impulses, the desire to know what lies beyond the horizon.